Okay, so let's start with the chemical properties. So they all can react in different ways, but one thing in which they react similarly is combustion. Combustion is the burning of a substance in oxygen with the release of energy. Okay, so if I take an alkane, CH4, I react with oxygen, and then I make carbon dioxide plus water. Every organic product that you have, or organic compound, will always react with oxygen to give carbon dioxide and water, provided there's enough oxygen. If there isn't enough oxygen, what happens there is we get carbon monoxide formed, which is toxic. Carbon monoxide irreversibly binds to the hemoglobin in the blood, limiting the red blood cells' capability of carrying oxygen around the body. So, provided there's an excess of oxygen, we always form carbon dioxide and water. Now, just in terms of balancing these equations, the first thing we always do is start with the carbons. We've got one carbon on the left, so we're going to have one carbon on the right. The next thing we do is we balance the hydrogens. Here I've got 4 hydrogens here, but only 2 here, so what I need to do is multiply that by 2. So now I've got 2 water molecules. The last thing we always balance out is the oxygens. So there are 2 oxygens in carbon dioxide, there are 2 oxygens now in water, that's 4 oxygens on the right hand side. So therefore what I need to have is 2 oxygen molecules there to give me my balanced equation. Remember, when you're balancing combustion reactions, always start with carbon, then do hydrogen, and then do oxygen. Okay, make sure you get the formula of the products right and the reactants right first before you start to balance them. So if you want to look more on combustion, you can have a look at the website. I'm going to now move on to the key difference between the homologous series and how they are made. Okay, so the alkanes we know are produced from fractional distillation. The alkenes can be produced by the products of fractional distillation by something called catalytic cracking, is where you break up long chain carbon molecules using a catalyst, quite often aluminium oxide, or also known as alumina, with heat to make alkenes. The other method for making alkenes is this system here, which is quite frequently asked actually. You take ethanol and have a little bit of glass wool just to soak up the ethanol here. You put it into a test tube and lie it horizontally, and you use a catalyst, aluminium oxide. And what you're essentially going to be doing here is dehydrating the ethanol. You heat the catalyst rather than here. You make sure there's no flames able to access the ethanol because it's highly flammable. What happens then is as the ethanol heats up, it forms ethanol vapors which pass over here. These in turn dehydrate and goes down a delivery tube, and what you form is ethene gas here. Okay, this is collected over water. Ethene isn't very soluble in water, so the gas will go straight through here and up into the test tube. A couple of things that you need to know about that. Question asked quite frequently actually is, in terms of preventing suckback, you need to keep the heat going and disassemble at this point, okay, before you remove the heat. This is known as a dehydration reaction because what happens is you take ethanol, which is another functional group, it's an alcohol, discussed later, you heat it with the aluminium oxide, and what you form here is the alkene. Now, a test for the alkenes is to add bromine, which we'll look at here. We know that bromine in itself is an orange liquid. If I add bromine to an alkene, what happens is the alkene double bond reacts and bromine adds across the double bond in what's known as an addition reaction. I should say that this is an elimination reaction or a dehydration reaction. So the test for an alkene is to add bromine, which is orange. Okay, so that is our test for alkenes. We know that an alkane won't do that because it doesn't have a double bond. Okay, so now what I'm going to do is quickly have a look in closer detail at the double bond of an alkene itself. So briefly I'll go through the chemistry of the double bond, and so this is really important because it can explain all of the chemistry that alkenes undergo. The story is more complicated than what I'm going to describe here because it does involve a hybridization of orbitals. They are atomic orbitals. That happens in all organic molecules, but we can describe it without actually going into the hybridization part of it because it's actually not on the course. So let's have a closer look at the bonding in ethene. In terms of this carbon here, we know that that carbon has got 3 atoms attached to it. Okay, now it's got one bond to a hydrogen, and that bond is just going to be a sigma bond. it's got another bond to a hydrogen, and that bond is also going to be a sigma bond. Now, a sigma bond is a head-on overlap of electron density. And for more on that, have a look at the covalent bonding section. Now, let's have a look at the carbon-carbon double bond. Well, if I look at the orbitals around a carbon, which are here, we know that in terms of the free orbitals that are available to each carbon atom, one of those orbitals forms a very strong interaction with the other carbon. It's no different to the other sigma bonds, and it's a head-on overlap of electron density. And that's what we have here, this head-on overlap of electron density. So it's a really strong bond, and actually that's the bond that's in all of the alkanes. Really strong head-on overlap of electron density. Now, the orbitals that are still free on a carbon after it's bonded to 3 other atoms, but has no other atom to bond to, no other different atom to bond to, that is. Okay, so the orbital that I've drawn out here is actually a p orbital. And because each of those carbon atoms have bonds to 3 different atoms, one of those bonds being to each other, there's a free orbital that has an electron in it that hasn't bonded to a different atom. Now, what happens is that orbital exists in a p orbital, and those p orbitals there and there cannot overlap in a head-on fashion. So they essentially just have to overlap in a side-on fashion, which is where we get our pi bond here. Now, because they overlap in a side-on fashion and they're not overlapping to a greater extent than sigma bonds, what you get essentially is a weaker bond. So pi bonds are weaker than sigma bonds, and as a result of them being weaker, they undergo far more chemistry. So they'll react more with other things, okay, and undergo different addition reactions and stuff like that, just like the one for bromine. So when I look at this here, we have our bromine system here. Bromine adding onto the double bond, it's actually the weaker pi bond that breaks, and bromine adds across onto it. Now, for more on the mechanism of that, see the mechanism section, and I will be putting up more videos on that later. A sigma bond is a head-on overlap, and a pi bond is a side-on overlap of electron density. Now what I'm going to do is quickly have a look at some other reactions that the alkenes undergo. So, alkenes are the primary source for all polymers. Now, a polymer is a long-chain molecule made from much smaller chains, monomers. There's different types of polymerization that occur. The only one you need to know in this part of the course is addition polymers. Addition comes back to alkene double bond, because we know that, and we've just seen that double bonds allow addition reactions to occur. That's atoms to just add across the double bond. Here, there's no difference in addition polymerization. What you need to know is that the double bond breaks, and they just add on to each other. So if I had 3 of them in a row like that, what would happen is the double bond would break there, and a new single carbon-carbon bond would form. And that's what happens. They form really long chains, so thousands of carbons long, and that gives rise to polymers. And polymers are essentially just plastics. We know that the problem with plastics these days is they don't biodegrade, because you form really, really, really long chain hydrocarbon molecules. Hydrocarbon molecules just have carbon-hydrogen and carbon-carbon single bonds, which are really hard to break down, so nature can't break them down using enzymes. We're left with a situation there that they can't break down, so therefore they get left and they get dumped in rubbish disposals, stuff like that. They end up out in sea, which, as you know, is a current global problem. So that's the main problem with plastics at this stage and polymers. Newer polymers are biodegradable, however, because we just incorporate some different atoms into the chain using a different form of polymerization, sometimes called condensation polymerization, which we're not going to discuss here, but you can make polymers biodegradable, which is great. Unfortunately, all the usual standard plastic bags that we have just contain carbon-hydrogen single bonds and thousands of carbons long, which can't get broken down in nature. Okay, so the last thing to discuss then in this video is going to be the alkynes and the formation of ethyne. Okay, so the formation of ethyne involves just using water and calcium carbide or calcium dicarbide, which is an inorganic solid which usually actually contains quite a few impurities. So we need to try and dispose of the impurities here using acidified copper sulfate. So all we do is use a dropping funnel to drop water slowly onto calcium dicarbide. What happens then is usually we instead of this diagram, which came from an old leaving cert paper, so we usually have another flask here in between the delivery tube that's used to take out all the impurities, and that flask usually contains acidified copper sulfate. The reason it's there is to remove the impurities like hydrogen sulfide and phosphine that are formed in the CaCO2. So all you're doing here is taking calcium dicarbide and using the water, essentially getting the hydrogens from the water and the carbons from the calcium dicarbide to create ethane gas. Again, it's done collecting over water using a trough and a beehive stand and a delivery tube because ethane isn't very soluble in water. Now, one thing you can do with the alkynes is you can test for them. One way of differentiating them and their other hydrocarbon counterparts is that they burn with a much smokier flame. So when you burn the alkynes and ethane itself, you get quite a lot of soot produced. So when your ratio of carbon to hydrogen atoms is quite similar, you get a much smokier flame. Whereas if you've got a lot more hydrogen atoms in there compared to carbon atoms, it burns more cleanly. So if you were to burn ethane compared to ethyne, you'd notice a very, very big difference. So what's going to happen is you're going to get a fairly standard flame with ethane, but there's going to be, whenever you burn the ethyne, you get a lot of soot, a lot of carbon produced, basically because of the carbon to hydrogen ratio. And that's pretty much all you need to know about the alkynes, is its preparation. Again, the only thing to note is that once you're using calcium dicarbide and you're adding your water to it, it can produce a lot of gas very quickly. The reaction is usually done and not all of them very pleasant, so the reaction is done in a fume cupboard. So that's it. We've discussed the alkanes, the alkenes and the alkynes. For more on their actual chemistry and the mechanisms behind the chemistry of the alkanes, such as free radical substitution, and the alkenes, such as addition reactions, look at the mechanisms for organic chemistry in the leaving cert section.